The first analysis you run of a complex part such as this hedge trimmer model may show that the part will not fill, or at least not easily, under default conditions. In this video, we will show you how you can improve the outcome. We discuss part design in the injection molding process, explain how plastic flows in a mold, identify the steps to take to optimize gate placement, explain what it means to limit changes in flow direction, introduce you to the idea of balanced fill pattern, and show you which process conditions you can change to optimize the analysis. The first consideration in injection molding is the part design. To shorten the cycle time, improve dimensional stability, and eliminate surface defects, a good guideline is to design your part so wall thickness is as thin and uniform as possible. The use of ribs is an effective way to achieve rigidity and strength while avoiding heavy cross-sectional thickness. Let's look at how plastic fills a mold so we can understand the impact of different variables. During the filling phase, polymer melt enters the mold and rapidly cools as it comes into contact with the cooler mold walls. The cooler plastic melt at the mold wall freezes, forming a solid layer of plastic referred to as the frozen layer. As additional melt flows through the center into the mold, it forces the flow front forward, which forms the next section of frozen layer as it contacts the cooler mold surface. As the rapidly moving core melt flows past the stationary frozen layer, the friction also generates heat. So the thickness of frozen layer increases until a thermal equilibrium is reached between the melt temperature, the frictional heat generated, and the heat loss through the frozen layer. It is important to ensure that the frozen layer in thinner sections doesn't increase too much and freeze through the thickness before the entire part is filled. The shear stress experienced by the material as it flows orients the plastic molecules in the direction of flow. The molecules at the mold wall are the most aligned, as they experience the most stress, and least aligned in the center. As the part cools, the orientation is frozen into the part. The orientation of the plastic molecules is important as it will impact the part warpage. So how do you think about optimizing gate placement? Let's start by listing the best practices, and then we'll see why they are all important. First, identify how many gates you will need. Then try to position them so that the melt flows without significant changes in direction. Finally, make adjustments so that all regions of the part fill at about the same time. What do we mean by balanced flow that doesn't change direction? This simple example shows that with a single injection location placed in the middle of a part, all extremities of the part fill at the same time, which is a balanced fill pattern, and the plastic flows radially without changing or reversing direction. The size of each contour should be about the same, indicating that the plastic is flowing in all areas at the same velocity, and no areas are likely to freeze too early. Use as few gates as possible and place them in thicker areas of the part for best fill quality. One gate is ideal. Add gates if the fill pressure rises much over half the machine limit, or to improve the fill pattern. If you don't know the machine limit, add a gate if the fill pressure exceeds about 70 megapascals. Now let's look at flow direction and balanced flow paths using a slightly more complex model, a paperclip. The fill animation result shows you the fill pattern and is the first result to check as you optimize your design. Which gate location provides for the least disruption in flow direction? The tip, center tongue, side, or end? It's easier to see the flow pattern if we switch to fewer colors in the contour plots. The answer is the end. With the gate located at the tip, the flow changes direction as it turns the corners into the tongue. Because the orientation of the plastic molecules is affected by flow direction, changes in this direction affect warpage and the quality of the final part. When the gate is located in the center of the tongue, the flow changes direction as it turns to fill the edges. The plastic reaches both ends of the tongue at about the same time. When it reaches the tip of the tongue, it has nowhere else to go except back. This change in direction is called underflow, and the accumulation of plastic at the tip causes overpacking. The overpacking in the tongue and the underflow both affect the quality of the fill. When the gate is located on the side, a weld line is created where the two flow fronts meet, and underflow at the weld line as more plastic is injected to fill out the tongue, creating a potential weakness in the arm and affecting the quality of the fill. When the gate is located on the end, there is no change in flow direction, but there is overpacking at the end of the tongue, which fills before the tip of the paperclip. So if pressure dictates that we only need one gate, and the end gate location is the best from the perspective of flow direction, how do we balance the flow so that all extremities fill at the same time? The fill animation result and the injection pressure result tell you how balanced the fill pattern is. To produce a good quality part, ideally, all areas equidistant from the gate are the same color, indicating that they filled at the same time. In this analysis, the tongue has filled when the arms are still only half filled, and the pressure is high in the tongue, indicating overpacking. We could move the gates to change the pattern, but we've already selected this position to minimize changes in flow direction. Molten plastic flows along the path of least resistance, so we can increase wall thickness to encourage flow in those areas, or we can decrease wall thickness to discourage flow. When we decrease the thickness of the tongue slightly, the pattern improves as the plastic flows more easily through the sides. The contours are beginning to match up in the fill animation result, and improving in the injection pressure result. In our next iteration, we could also try increasing the thickness of the arms slightly. What does this mean for a more complex part, such as the hedge trimmer model we saw at the start? The pressure indicates we only need one injection location. The fill pattern is similarly balanced with one gate on the side face or the top. Although when we switch to the injection pressure result, you can see that the pressure is at the top of the feasible range using the side gate. With the gate on the bottom face location, the fill time is too long. And closer inspection shows it's short shots. That is, the plastic freezes before it fills the location of the short shot. Regardless of the gate location, it appears that there is likely to be a problem with this thin rib. If you can't edit the model, you can try adding another injection location. A second gate on the side opposite helps to fill that short shot location. A second gate here reduces the pressure compared with the single location, but the low pressure indicates that the plastic freezes too quickly on this rib, and that the real problem is its thickness. If you can edit the model, you can increase the thickness of that rib, or decrease the thickness of nearby ribs. When we increase the thickness of the rib, the part fills more readily and more uniformly, but the pressure is still higher than ideal. How can we decrease the pressure without further changes in the design or gate placement? Let's review the variables we can change to optimize the filling. We've talked about the part design and the injection location, the material you select, and the settings used to process the material in the injection molding machine can also affect if the part will fill or not. That is, the melt temperature, the mold temperature, and the injection speed. Some plastics push like cement, and others flow like water. This affects the pressure and how many gates are needed to fill a part. The temperature of the molten resin affects how well it flows and how long it takes to cool. The hotter the material, the more easily it flows and the further it can be pushed. But it requires more energy to heat and takes longer to cool, which increases the cycle time and costs more to produce. The temperature of the mold affects how quickly the material cools. Finally, the speed with which the material is injected can have a large effect on the pressure required to fill the part. Too fast or too slow, and the part will not fill. When we decrease the injection speed, the pressure decreases slightly, but the rib freezes too early. As expected, increasing the speed increases the pressure, which is not what we want. Increasing the melt temperature means it flows more easily, significantly decreasing the injection pressure. In this video, we discussed part design in the injection molding process, explained how plastic flows in a mold, identified the steps to take to optimize part filling, explained what it means to limit changes in flow direction, introduced you to the idea of a balanced fill pattern, and showed you which process settings you can change to optimize the analysis.